this over now to Everett. And Everett is a pretty well-known guy in his field of exoplanets and looking at the atmospheres of exoplanets. And he has done this by using data from space-based observatories like the NASA Kepler mission and in the future, the JWST, which he will tell you all about. Everett?
All right, thank you, and thanks for coming. So today I'm excited to talk to you about the finding ingredients of other worlds and how we can do this with spectra. So I want to take this time to just acknowledge some of my teammates who are working on this James Webb Space Telescope. My boss is Marcia Ricci, who's in charge of the main camera on the telescope. And then we have this team here at the University of Arizona that all work on this camera. Some of the people I've stolen slides from are also listed below. So I'm going to begin by telling you about my story of how I got interested in astronomy. And that was in high school, at probably about the same age as many of you now, where I was able to borrow a telescope and went out with my dad and pointed this telescope at a bright thing in the sky. And what we saw is this donut-like thing in the telescope. And I was like, that's weird. Start turning the focus knob and turning it and turning it. And it got smaller and smaller, and the donut got smaller. And then, boom, this thing popped into the telescope. It was Jupiter. It's just beautiful seeing these bands going through Jupiter. And I thought, that's incredible. We can just see this in a backyard telescope. I want to do more. I want to find out how we can keep doing this and do astronomy as a career. So that's what got me hooked. So in high school, I like to go out and do kind of backyard astronomy. Later built this telescope and ground the mirror for fun to make this hobby and be able to do this hobby. So when I was in high school, I focused on physics and math and went to college in Oberlin College in Ohio, where I was a physics major. And I was also able to spend some time at the observatory there, taking pictures of different objects. This is a picture I took of the Andromeda galaxy when I was at Oberlin College. And from there, I applied to graduate school and was accepted to Cornell University, where I got my PhD. I did a mixture of doing science of exoplanets and also building this instrument, which is called Arco-Iris, and it now lives in Chile on the Blanco telescope there. When I got my PhD, I moved on to the University of Arizona, where I am now. I'm on this James Webb Space Telescope team. And I also use the ground-based observatories. Here's the large binocular telescope, which I've used as well. And in Tucson, I've been able to raise my son and try to get him interested in the night sky as well. So that's my story. Now I'm going to tell you the story, this journey of the Webb telescope. It was put together, and I got to see this in Maryland at the NASA Goddard Space Flight Center. And from there, it was shipped to Texas at NASA Johnson, where we tested the optics of the whole system. And when those tests were completed successfully, it was moved to California, where it is now at Northrop Grumman, and where the telescope is combined with the spacecraft in order to complete this spacecraft and observatory. And from when the testing is done of the James Webb Space Telescope, it will be shipped by boat through the Panama Canal to French Guiana, or will be launched on an Ariane 5 rocket. The next shows a zoom out of its journey through space. It'll take a few weeks to travel to its point in space, where it's going to do its observations of many interesting things, from galaxies to planets, and make its observations, bring us new science. So this video made by Northrop Grumman shows what the unfolding process will look like in the James Webb Space Telescope. So for the first things that happen is get the solar panels out to power the observatory and the antenna to communicate. Now it's unfolded these pallets and uncovered the sun shield. Right now it's pulling apart the sun shield. This sun shield is a critical part of the observatory that keeps the sun-facing side at 190 degrees and the cold side where the telescope is to minus 390 degrees Fahrenheit. So this is kind of fire and ice from one side of the other telescope to the other. In order to keep that side face that's doing the science, the telescope cool, it has to have this 5-layer sun shield. So right now you're seeing those layers separate, and it's important that you don't conduct the heat from the sun down to this cool side. So that's why those layers have to separate and not touch each other to efficiently bounce that heat away from the observatory. And then finally, the mirrors are deploying, and you have the complete observatory. So why do we have to keep this telescope so cold? And the reason is that everything warm is a light bulb in the infrared. So infrared astronomy senses heat. And even humans, you and me, we are light bulbs in the infrared. So you want to do everything you can to get rid of that warm radiation from the Earth, the Moon, the Sun, and keep the observatory cool. And the way it does that is it lives at this special point in space called L2, Lagrangian point 2. And this shows a little bit what it looks like, the orientation. So this is a special point in space that allows you to follow the Earth's orbit in a 1-year orbit and always maintain that sun shield facing the Earth and the Moon and the Sun, keep that heat away from the telescope. And there are other Lagrangian points too. But this is the best one where many telescopes actually live, and there's plenty of room there, so they're not going to run into each other, but it's a great place to put an observatory that senses heat. So now we're going to move on from that journey to what the science that James Webb Space Telescope can bring us on extrasolar planets. Now, this was possible by the discovery of previous observatories of the planets that are out there. And one of the missions that found the most planets so far is the NASA's Kepler mission. And what this mission did was stare at a patch of the sky near the constellation Cygnus and basically stare at it without blinking, waiting for planets to cross in front of their stars, and then measure that little wink in light to see the planet's presence. So this is done by NASA's Kepler mission, and boy, did it find lots of planets, many, many thousands of them. So this shows what would happen if you were to bring all those planets in one spot. It's a visualization of their orbits compared to the solar system. So you can see the solar system planets here, and that all these planets that Kepler found, the vast majority of them have these really, really tight orbits. They're kind of unlike anything we have in the solar system. So that was one of the big surprises with extrasolar planets, is that not every system is like our solar system. There's a whole beautiful variety of different planetary systems, and many thousands that are out there. We now know that there's more planets than there are stars in our galaxy. So there are 100 billion stars in our galaxy, and even more planets that could be potentially interesting places to study. And so that's the Kepler Observatory. There's another mission called TESS, which is doing the same thing and finding even closer ones that can be used to study. So the planets that we're talking about today, these are called transiting planets. That means that they go in front of and behind their host stars. So this enables interesting science of their atmospheres because we can use different points in the orbit to study the planet. So the first point we're going to discuss is the primary eclipse, where the planet's in front of the star, where you can study its composition. The way you do that is with a spectrum. And what we astronomers use is a variety of tools. The simplest one is a prism to spread the light into its component colors or wavelengths. So here you can see this artist rendition of the light going through a prism and the different colors that come out. So those are the colors you can see, but there are also wavelengths of light that you can't see. So there's a very simple demo. You can do this at home with a remote control. You can see that there's actually, with the camera is sensitive to light that your eyes aren't. So this is infrared light for a remote control, near infrared light. But there's this whole electromagnetic spectrum, all sorts of different light that our eyes are not sensitive to. And so telescopes can record those interesting wavelengths of light. And we can analyze a spectra. We're going to see different kinds of spectra today. So there are three main groups of them. The first one is a continuum spectrum, where you have this light source that produces this broadband rainbow spectrum. The second one is an absorption spectrum. So between that light source and our observations, there's a gas cloud that has absorptions at specific frequencies. And those produce these dark lines on top of the rainbow. And then thirdly, there are emission spectra, where the gas cloud is emitting and it's brighter than its background. It has these emission lines, so these bright lines against the dark continuum. So these are the three kind of spectra we're going to see today. And now we're going to do kind of an interactive activity where you are in charge of identifying this gas. So normally we do this with a lamp and these cool spectra glasses. And right now, Connie's set up a poll, so you should see a pop-up here where your job is now to take a look at this mystery spectrum. So this is a picture I took with the camera. I took a picture of what your glasses would see, spectra glasses would see, and then what you need to do is match that mystery spectrum to a spectrum library. So here are some laboratory spectra that have been measured, and also you can calculate theoretically what these spectra should look like. So now your job is to go to this poll and see within that mystery spectrum, what gas from the library can you see? Why don't you take maybe 20 seconds or 30 seconds to make your vote on what you see. And if you don't see anything from the library that's in the mystery spectrum, you can vote for that. This is indeed a picture of the hydrogen spectrum, and it has those two bright lines. Now, you might notice that the template has some purple lines that don't show up in the mystery spectrum, and this is what happens in astronomy. We don't always get all wavelengths at once. Sometimes we just get a piece of them. So this is what happens with observations, where sometimes you just get chunks of the spectrum that are there. Okay, so that was mystery number. Let's try another one. So I'm going to ask Connie to clear the poll, and we're going to do mystery number 2. So I also see a note here that the double yellow lines best match. Yeah, so there's only one spectrum in the library that has the double yellow lines. So what you're seeing here is that each chemical has its own unique chemical spectral fingerprint that allows you to figure out what's in the mystery spectrum. This is what astronomers do. They just work with the light. There's no ability to go there and take a sample and bring it back to the Earth. These are far beyond what we can travel to, these planets. And so all we have to work is with the light, and you are doing just what astronomers do, figuring out what's in these atmospheres using a spectra. And we're going to do mystery number 3. What gas from the spectrum library do you see in the mystery spectrum? I think a lot of you are noticing that there are multiple spectra in this mystery spectrum, and that's what happens. This lamp happened to be contaminated. So this is helium indeed. So if you voted for helium, you're right. But also, it's good to be noticing that there's a contaminating gas in there. So that can happen. These lamps over time get contaminated with other gases. But this is giving us a little bit of clue of what happens when we look at a real exoplanet atmosphere. There can be multiple different gases in that atmosphere that we need to identify. So this is kind of giving you a sense of what astronomers are trying to understand with extrasolar planet atmosphere. So astronomers don't typically look at the rainbow spectra that we've looked at today. They did once upon a time in the early days, but now it's done through plots. So the plot is just containing the same information, but it turns it into a plot where the x-axis is wavelength and the y-axis is brightness. So this is nowadays what astronomers use to identify spectra. And when they do this, here's a rendition of what it would look like with the planet going in front of its host star. We can't see the planet against the star because they're too small and far away. But instead, what we do is measure this spectrum of the light from the star that gets absorbed by the planet. And you can see that there's this methane signature in the spectrum of the planet. That tells us what's in this atmosphere, what this atmosphere is made of. And what we can do with that information is learn about how planets form. So we now are learning that planets form in these protoplanetary disks that have the materials to build planets, and we can learn from the atmospheres of planets a little bit more about that process of planet formation. And the way this is typically done is to build a model. So you start with a model for that disk surrounding a star that has planet building material, and then try to figure out what the planets that it makes would look like. There's a growing consensus now that planets are made in these disks when this icy and rocky material starts sticking together. They basically stick together and stick together and grow until they become these planetesimals, and those stick together to make a rocky type planet. And the process can stop there to make a rocky planet, but if it keeps going and that rocky planet is 10 Earth masses or larger, then it has enough gravity to suck the gas in from its surroundings to become a giant planet, which it has a gaseous envelope surrounding that solid core. And so what we can do with these models is figure out where the material is going and how much you expect to show up in that gaseous envelope from the planetary building blocks that you can compare with your measured spectrum. So that was a lot about the primary eclipse and what you can do with the spectrum of the primary eclipse. The other thing you can do is look at the secondary eclipse when the planet's going behind its host star. And this is where you learn about the temperature in the atmosphere. Where is it hot, where is it cold? In Tucson, we're very familiar with heat. We know in this Tucson summers, it's very hot down below, but if you go up, so on the left, when I'm talking about a temperature that decreases with height, you go up to the top of the mountain, you can get some relief from that heat. As long as there are no wildfires up there, you can go and cool off a little bit in the summer. So we're familiar with this kind of temperature, it decreases with height, but you can also have a temperature inversion where it gets warmer as you go up. And this can happen in some places, and this is in Hawaii, where there's a temperature inversion where the heat tends up to, it gets pushed at higher levels, and so when you go up in altitude, it actually gets warmer. So this is called a temperature inversion. It's a more stable situation because the hot stuff on the top goes up, the cool stuff on the bottom sinks down, and so you get a more stable configuration than a temperature that decreases with height, where the warm stuff on the bottom wants to go up, the cool stuff on the top wants to sink down, and goes circulating, bird. You can figure out how this atmosphere works. Was it hot on the top and cool on the bottom? And this is an example of the solar spectrum. When you look at the spectrum of the sun, you spread out that rainbow of colors from the light from the sun, you get this rainbow continuum, and on top of it, these dark lines. And those dark lines are absorption from a cooler gas. And so this teaches us that the sun's atmosphere, this photosphere we see from the sun, is cooler on the top and warmer on the bottom. So you get these absorptions. You can also see from the spectrum the temperature inversion. An example is the neon emission lamp we saw briefly, where we had that hot gas surrounded in front of the dark background. So if you see the emission lines that are going up, then you can figure out there's a temperature inversion in a planet. So that's a little bit about what you can learn from a secondary eclipse. You can also learn about the planet by following its light as the planet goes around its orbit. So we get this orbit, full orbit of the planet. You can measure the light from the night side to the day side. And you can figure out where the hottest part of the planet. You can make a map of a planet as it goes around its orbit. And this was also can be compared to predictions. So there's an astronomer that was here, Adam Showman at the University of Arizona, that ran a great theoretical calculation for where the heat will go in this kind of hot Jupiter atmosphere. What his model and his team's model predicted was that the winds will carry that heat eastward from the solar noon point. And so you can see that off spot. So they went out to measure this phase curve, as it's called, and compared to this model, and they found that his model was right. So that was a great example of the scientific process where you make this hypothesis and you test that hypothesis, and this example, the hypothesis was correct. So we've discussed how spectra are a valuable tool. It's a valuable tool to understand the composition, how planets are made, make maps of planets, and understand whether it's hot or cold as you go up and down. And this is going to be done with the James Webb. But you might be asked, so these are really interesting scientific questions, but you might be in your heart interested in a deep question that I see in the Zoom chat. I see also that many science fiction authors and movie makers have asked, are we alone? It's a big question that many of us are asking, and it's captured our imaginations. Well, we can start to learn that from extrasolar planets and their atmospheric spectra. So this is an artist's rendition of the TRAPPIST-1 system, and it's actually a poster. You can find these posters, and TRAPPIST-1e is one that's probably the most like Earth in its temperature, but it's a 7-planet system orbiting this red dwarf star. So I'll just say that these posters are really cool. You can download, you can print them yourself, and I think Allie has an example of some of them she can show. You can download it. So here's the link, or you can pull up your phone to this QR code to get the link. And this is another extrasolar planet. It's kind of a lava world. Not great to go there, but it's a very warm planet and cool place. So back to the TRAPPIST-1e system. There are 7 planets in this system that orbit a small red dwarf star. And actually, the red dwarf star is not much bigger than, this is the relative size of that star and Jupiter. So it's not much bigger than Jupiter. And the reason astronomers are so excited about this tiny star is it makes it easier to study the planets around them. When you compare that Earth-sized planet to the sun, it's very hard to find the signals. But when you compare that Earth-sized planet to this red dwarf star, it's easier to detect. And so what astronomers are interested in this system, one of the things they're looking at is the habitable zone. And what that means is when you get really close to that host star, it gets hot. If you move farther away, it's a bit cooler. And so just like with a campfire, you get up really close, it's hot, you move farther away, it's cool, but there's this nice medium where it's comfortable in between, this Goldilocks zone called the habitable zone, where water could be liquid on the surface. So one of the things we can do for these habitable zone planets, like 1e, is to study whether it has atmosphere. So the first question we can ask is, does it have an atmosphere? So you can look at the colors on the right. If it doesn't have an atmosphere, we just get this opaque circle, and it's the same at all wavelengths. There's no color dependence. But if it has an atmosphere, what we can see is a color dependence. The red light gets through. Just like when you look at the sunset, the sun looks red because that red light gets through better. The blue light gets scattered away. It's the same reason we get the blue skies, the scatter. So we can answer first, if it has an atmosphere, then maybe someday, it's right at the limit of what the James Webb Space Telescope can do, but maybe a future telescope is to search for Earth that's like, search for life that's like the Earth. If you look at the Earth's atmosphere, that you can see that there's some chemical products from organisms on the Earth. We have photosynthesis from phytoplankton and trees producing oxygen, and we get methanogens that are producing methane. And this, without life, the Earth, you just wouldn't see any methane and oxygen in the atmosphere. They react quickly. You need life to replenish those. So you can look at a spectrum to find these. So here's an example transmission spectrum for the Earth, where you have the methane signature and an oxygen signature, which gets turned to ozone at the high altitude. So the way I view James Webb's Space Telescope's role is a stepping stone to life detection. We need to learn what planets are made of and how they form, which rocky planets have atmospheres, and understand where the heat is distributed in those atmospheres to lead to the future where we can search for Earth-like limit with future telescopes. So this is the journey of the Webb telescope. Thank you for coming on this journey with me. The Webb telescope will be coming to a Lagrangian point near you next year. Is when the launch is planned. So stay tuned, and thank you for your attention for this presentation.